Hey everybody, Mr. Plant here. Today we are going to talk about the models of the atom. We're going to start 440 BCE, 2500 years ago, and work our way forward in time until the current day. So our first model of the atom came from a Greek philosopher named Democritus. He was a guy that just kind of sat around and thought about the way the world works. One of the things that he came up with is that everything around us is made up of building blocks. That if you take a rock and you cut it down in half and in half and half and keep cutting it in half, eventually you get to the smallest part of a rock that you can't cut in half anymore. And he called this part of the rock an atomos. Atomos was a Greek word meaning uncuttable or indivisible. So if you get to that point of the rock that you can't cut anymore, boom, atomos. And that's where he kind of stopped. Right? He said that things like clay were made up of clay atomos, that metal was made up of metal atomos, and all wood was made up of wood atomos, and so on and so forth. But nothing much more. So flash forward to 1803, over 2,000 years later, and no one's really thought about the model of the atom until John Dalton comes around. He's kind of the father of modern chemistry. He did a lot for chemistry in his time alive. And he came up with the billiard ball model. So I put a picture here next to him of a billiard ball, right? This kind of orange-red 5 billiard ball, or pool ball, you might know it by. So he kind of brought back Democritus's theory, but instead he called these small particles atoms. And that's kind of where we get our modern day name for them, atoms. He thought atoms were solid like billiard balls, that they have one part, they're just these solid chunks, and that they can stick to and bounce off of each other. Where he built on Democritus's theory was these three important conclusions. Number one, atoms of the same element are the same. Different atoms means it has to be a different element. So iron is made up of iron elements, iron atoms, right? The element nickel is made up of nickel atoms. That was a big idea. Number two, he said atoms are the smallest particle and cannot be broken down further. He was wrong here, but we'll talk more about that later. And then three, atoms join in certain combinations to make new substances. This is how we get things like water. There isn't an element water. There's hydrogen and oxygen, and the combination of these two makes a new substance, water. Pretty crazy idea for how little he had to work with. So another 100 years go by, and J.J. Thomson comes along, and with experimenting with cathode ray tubes, he finds out that the atom is actually a little bit different. And so he creates the plum pudding model. Here's a picture of plum pudding. It's an English dessert. It's kind of like a sponge cake with plums in it. You can also think of a chocolate chip cookie. So he used these cathode ray tubes and experimented with them. And the only way he could figure out that what the cathode ray tubes were doing, why they were behaving the way they were, was that the atom has two parts. It has a negative part and a positive part, like the negative part of a battery, right? The flat end of a AA battery, and then the positive part, the nubbed end of a AA battery. He thought that the atom was mostly positive space, and that just had these little chunks of negative pieces that we call electrons to this day. So it was mostly, if you think of a cookie, right? It was mostly cookie with little chunks of chocolate chip, or in this case, mostly electrons. Well, a couple years later, Ernest Rutherford performs this amazing experiment, kind of ground-shattering experiment with gold foil to create the planetary model. Okay, so he took radiation, specifically alpha particles, which we don't really know about yet, but we'll find out more about them later. And so he shot these alpha particles at a thin sheet of gold, and it was surrounded by a screen. Now, Rutherford's hypothesis, right, what he thought was going to happen was that the alpha particles should pass straight through the gold, and he should see them hitting the sheet on the other side. But instead, the particles would ricochet and deflect every now and then. The only way that he could explain this was that the alpha particles were hitting something solid, and that eventually this led him to finding out that the atom is mostly empty space because a lot of the radiation, a lot of the alpha particles pass straight through, but every now and then they hit something, and that something was a positively charged center called the nucleus. Just like in biology, the center of the cell is the nucleus, the center of the atom in chemistry and physics is the nucleus. This led to the creation of the planetary model, where you have negative electrons that just kind of fly around the nucleus of the atom, right? They kind of didn't know. They're like, whatever, the electrons are out there. And that in the center was the positive nucleus. Just like the planets go around the sun, but he really didn't even say they had like a set path. He just kind of said they flew around the center, the nucleus. So a couple years later, Niels Bohr comes along and he does a lot of fancy experiments to find out what those electrons are actually doing. Okay, and so he finds out that electrons have to travel in certain areas based on their energy. So he said that negative particles, the electrons, traveled in paths called energy levels or orbitals. Right? Orbit, like you orbit around the Earth, and orbital is just the path. Okay? In his model, the nucleus sat at the center of the atom, made up of some protons and neutrons by this point, and that the electrons orbit in these different energy rings, and that each energy ring can only hold a certain number of electrons. Okay, this model of the atom we call a lot of times the Bohr model of the atom, but you'll also see it called the energy level of the atom. It was really close. This is also our best way of drawing atoms out to show what they're doing, but it's not quite right. So a couple of years later now, Werner Heisenberg, a German scientist, comes along, and in 1925 he discovers that our model of the atom is actually a little bit different than Bohr's model of the atom, specifically how these electrons behave. You see these crazy shapes, these like red balloon things. Those are orbitals and kind of probability states, which are these big fancy words that we'll talk about. Okay, so he discovered our current model of the atom, where we have a positive center, the nucleus made up of protons and neutrons, and that we have negative particles called electrons that surround the nucleus in an electron cloud. Now, this idea of the electron cloud was kind of weird, and it is a hard thing to wrap your brain around. So here's a way to think about it. We can only predict where we think electrons most likely are. We have no way of knowing for sure where they're at. We just think that they're there or not. That's kind of weird, right? So we just have these areas where, based off the energy of an electron, we can say, hey, it's most likely in this area around the atom, but we don't know exactly where. And that's where we get these cloud shapes. If you look at the picture in the bottom right, we get these fuzzy areas where we're kind of saying, okay, this is most likely where electrons of this energy are hanging out. This ends up being our most accurate model of the atom. And we call it the electron cloud model because of how these electrons behave. It's pretty similar to Bohr's model, but when you get into some advanced chemistry and particle physics, it starts to explain things way better when we use the electron cloud model. So it's important for us to know this is the most current model, but that we'll probably use Bohr's model to represent models of the atom. All right, guys, that's it for today. I'm going to attach a example of my notes to Schoology, and so you can see what your notes should look like, and we'll probably go over it in class as well. But be taking good notes. Make sure you're adding pictures. You're getting everything you can to make sure that you're remembering this information so that when you come to class, we can talk about it and you can ask questions. All right. See you guys later.